Okay, so we're ready to talk about a thermodynamic variable known as enthalpy. And it's probably the most important variable that we use in this class uh, for calculating energy. And the enthalpy is actually the heat released by a reaction when it does any kind of work. Okay, so it's the amount of really available work, energy for doing useful work that's part of a chemical reaction. So we give it the symbol H, and really what we're most interested in is the change in enthalpy, delta H. That is the energy a reaction starts at and then the energy it ends at. So the final energy minus the initial energy. And again, this has to do with the amount of useful work that you can get out of a system. So it was defined as E plus P times V. And there's lots of speculation as to why it was sort of listed this way. But part of the way of thinking of it is E is the internal energy of the reaction. So this is the energy in a reaction, or in this case, energy of a state. And this is the work of a state. But if you look at the change in enthalpy, then the delta H is going to be equal to delta E plus delta P times V. Okay? And one of the things that they like to do is they like to say, well, let's look at this at constant pressure. And that's what this means up here. So when we have at constant pressure, we can write the following. Delta H is equal to delta E plus P times delta V. So we do this and we pull it out from the delta. The delta is just final minus initial because it's a constant. So if you had a constant times a volume and then you did a delta of that, it would be C times V final minus C times V initial, right? And C would be a constant, and then you can factor that out and say V final minus V initial. Well, this is what we did with pressure over here. We just said, well, we have a pressure which is the same in the final and initial states, and we do the change, right, delta V or delta P times delta V, and then we can extract the constant out of here, which in this case now is pressure. We just say the pressure doesn't change. Okay? All right, so when we do that, we can take a closer look at this, and we put the subscript P when we do that, and we put the subscript P here. Delta E, right, the change in internal energy, we talked about him before, is equal to Q plus W, and that's equal to delta E is equal to Q minus, and then W has that further definition as minus P delta V. So we're going to say minus P delta V here, but look what happens when you substitute this into here. You have delta H at constant pressure is Q minus P delta V plus P delta V, and that's just equal to Q. Okay, so enthalpy is the energy available to a reaction when it also is by itself doing work. It's the available amount of energy to do like work itself. Okay, like for example, drive a piston, things like that. Okay, so let's sort of look at what kind of, let's look at some of the properties of enthalpy. So when we're talking about chemical reactions, when we say delta H is positive, that means the reaction is absorbing heat energy. So energy is going into the system, and we refer to those as endothermic reactions. And when delta H is negative, these are reactions which are releasing energy, right? And when they release energy to the surroundings, we refer to them as exothermic reactions. So when we talk about endothermic and exothermic, specifically, we're actually talking about the enthalpy of a reaction. So enthalpy behaves, or sorry, let me say one other thing. Enthalpy is an extensive property of the system. So what does that mean, right? So let me show you this next problem. Okay, so back up for a second. One of the properties is that when we say delta H is positive, it's endothermic, delta H is negative, it's exothermic. And one of the properties is also that it's an extensive property of a chemical reaction. And what that actually means is that the amount of energy that you get out depends on the amount of material you put into the reaction. Kind of know this intuitively, because if I put a gallon of gas in your car and you drove a certain distance, right? Well, let's say I put 2 gallons of gas in your car and you drove a certain distance, let's say it's 60 miles, and I said, here's a gallon to get back. What do you know is going to happen, right? You're going to run out of gas about halfway home, right? That's because the amount of energy in the gasoline is dependent on the quantity of gasoline that you have. So the amount of energy available from the gasoline, I should say, is dependent on the amount of gasoline that you have. So here's a calculation. It says, calculate the heat energy released when 10.3 grams of propanol, that's this substance here, is burned. Okay. Now, you'll notice that I've written, this is the enthalpy of the reaction. And there's the propanol, right? And you know from stoichiometry, like if you burn 2 moles of propanol, 9 moles of oxygen is consumed, or 6 moles of carbon dioxide are produced, and things like that. But it's also true that when 2 moles of propanol are burned, right, it produces 4,011.2 kilojoules of heat energy. And the negative means it's exothermic, right? Products are going to a lower energy state and energy is being released. So we can use this enthalpy just like we use other stoichiometric coefficients. It's like the 4011.2 negative is the coefficient for kilojoules in the reaction. So what we're going to do is, to solve this problem, if you want to know the energy released from 10.3 grams, we're really looking for Q, heat energy. And that's going to be, I'm going to start with grams. This is just going to be the problem-solving map. So let me go like this. I have grams. I'll go to moles. And then I'll go from moles to kilojoules. Okay, so let's do this. Q is equal to 10.3 grams of C3H7OH. And now I need to convert this over to moles. So I need the grams at the bottom, right? And I need the moles at the top. So the molar mass, if you calculate it, is 60.095. And this is how we use the enthalpy in the calculation. You'll write negative 4,011.2 kilojoules for every 2 moles of C3H7OH. And that gives us a value of negative 343.8 kilojoules. So again, right, just like a normal stoichiometry problem, when you're given grams of something, you can convert it over to moles of anything, or now you can convert it over to kilojoules of energy. So here's another problem for you to practice on, right? It says titanium reacts with iodine to form titanium 3 iodide, so that's the reaction here, and balanced, emitting heat, and there shouldn't be a hyphen in there. But and there's the reaction, and there's the energy associated with this balanced reaction, right? Determine the masses of titanium and iodine that react if this many kilojoules of heat is emitted by the reaction. Okay, so think about how you're doing this, and then go ahead and pause and work through it, but I'll give you a starter on this, right? Now you're starting with the energy. And the energy of the equation can be used to convert to moles of two different substances. Now that's two different calculations, right? And then once you have the moles of substance, then you can convert it into grams. So your pathway is going to be kilojoules to moles to grams. And it doesn't say what unit, so we'll go ahead and stick with grams. So go ahead and pause it, and then when you start, I'll have it all worked out on the slide, and we can discuss how it's done and the answers themselves. Okay, so here's those solutions, and probably some of you are wondering what to do with the negative sign that's in the problem, and really you just leave it, and then I'll help you interpret what that means. But it's 155 times 10 to the third kilograms. Then it's 2 moles of titanium, kilojoules. It's 2 moles of titanium for every 839 kilojoules of energy, like here. That's this mole ratio here. And then it's 47.867 grams per mole for titanium, and then you get a negative 166 grams of titanium. So what does the negative mean? It means it was used up. Now, I will tell you, most of the time when you're doing problems like this, they don't want the negative sign for the amount of material used. But when I do the problem, I get a negative sign. I don't even think about it now. I just say, well, that's how much was lost. That's how much was consumed in the reaction. Okay, same calculation for iodine. The only differences are that there's 3 moles of iodine and its molar mass is much higher. So you end up with, almost 10 times as much iodine in terms of mass. 1.41 times 10 to the third grams of iodine get used in this reaction. And like I said, if people ask you for this, it's on a quiz or whatever, don't include the negative signs with these masses. But that's actually comes out of the calculation. So that's what that means. That's how much gets used up.